Okay, so what we are planning to discuss today is so as you know, this course is on electromagnetic theory, and we have been uh, okay. Hi, okay. So we are just starting. So we have been talking about Maxwell's equations, about magnetostatics, electrostatics, and all of them. What we now want to do is we want to look at a very important application perspective of electromagnetic theory and look at a case where, so when we talk about one of the major applications of electromagnetic theory comes in circuits, right? But then when you have some circuits or some kind of networks, there most of the cases in our day-to-day lives, we don't take into consideration the effect of the connecting wires. Okay, so in this current class, what we'll try to look at is what are the situations in which we can ignore the effects of the wire, and under what conditions wire, like the properties of the wire becomes important and one needs to consider them. Okay, because what is a wire or any kind of connecting leads, these are all a kind of they have some, they are basically conductors, right? And they can have resistive uh, properties, they can have inductance, they can have, so when current flows through them, they can have inductance. Then they can also have some capacitance if you have multiple, if there are two wires. Okay, so then there can be a capacitance between them. So in this present talk, we want to see that under what conditions these these parameters that describe the wire or the connecting leads become important, and one needs to consider their effects. And how do we consider their effects? Okay, what changes do they bring to our estimations and calculations of our circuits? Okay, so that's what is today's class about. So we will do some we'll discuss the basic concepts, some problem solving, and if you have some doubt, you can ask me. Okay, so to start with, initially, as you can see, uh, what is a lumped system and what is a distributed lump circuit and distributed circuit? Okay, so if you think of whatever we generally talk about, okay, in those cases, those are all lumped circuits. What we mean by that? So if you look at the picture, you'll understand that. See, if suppose this is your signal and you have some element, okay, if it is a wire or some coax or something, just think of it as some element. And now this is the current that is entering and this is the current that is leaving the this element. Okay, now normally, suppose if you have a resistor here and then the current flows from here to here, then there is something else here. We don't look into, or we don't consider that there is any change in the current or voltage in this region, right? In the wire, while the current is flowing in the wire, or while there is a voltage transmission through the wire. So suppose if this is the incident current and this is the reflected current, this is the transmitted current, like that the current that comes out from this element, this is how it looks like, right? So there is not no much change, and no, so you can see that the moment it's here, at the same time you'll see the a similar signal at this end, right? So this is what happens in our normal day-to-day circuits, right? Where or the cases where we apply Kirchhoff's law and all that. So this is called a lumped circuit. Okay, but now one can have another kind of circuit where what happens is, now this is your some starting point. Okay, you know the current here. This is given by this signal here. Now there's a connection lead. Okay, then there's some lumped element where we have considered that there is no change here and here. The incident and the current that is leaving this element is same, but then it travels through this connection lead and then reaches some point B. Okay, so what is seen is that in certain cases, what can happen is when when you see the signal here and then when you see the signal here, you see that there's a delay between the two, right? And then that delay is actually function of the length of your connection leads that join the 2 points, right? So when this kind of cases happen, then it's actually a distributed circuit. Why distributed will come soon, but the basic difference is that now the connection leads make a difference. The connection leads cause delay. and that depends on the dimensions of your connection leads. Okay. So if we think of the different regimes, there are these different kinds of regimes like the lumped circuit regime or the optics circuit regime or the transmission line regime, which we will discuss today. So what is the major difference between all of this is, as you can see, that in our normal day-to-day circuits that we do, or in the cases where we apply Kirchhoff's law, what we consider is that there's no change in voltage or currents over the connecting wires. Okay, so there, why is it appropriate to do that? It's because the physical dimensions of these components, of the various components, are much smaller than the wavelength of the signal. Okay, so we don't have to consider the changes that happen while the transmission is taking place through the connecting wires. So this is called the lumped circuit regime, and it's basically the electrostatic limit of the situation. Okay, so where we say that the surface of the conductors are equipotential surface, and there's no change in moving some charge from one point to another over the surface of the conductor. Okay, and in this condition, what we do is here the Kirchhoff's law is applied. And as you can see, because the wavelengths are much larger than the dimensions, the wave nature is ignored. Okay. But then there's another regime where what can happen is that the dimensions are much larger than the wavelength of the signal or wavelength of light in general. In general, it's a signal, or you can consider light just for your, for your intuition. So there, what happens is we are actually similar to the ray optics regime. So it's a regime where we can consider the waves as rays, and there, as you can see, even in those cases, we already know that they, for optics there's a ray optics regime, there's a wave optics regime, right? So, and in these cases, your Maxwell's equations become much more simpler. But then what's interesting and what we'll try to discuss today is this regime where the dimensions of the components are actually comparable to the wavelength of signal. So when can these things happen? So suppose when you are talking about microwave circuits or cases where your frequencies are way higher, suppose in the gigahertz range. So there, now if you calculate the wavelength, it comes around some 30 centimeter, right? So now if you are connecting wires or the components that are there, if their dimensions are of the range of this value, so suppose some 10-15 centimeter or something, so then their effects will come into picture, right? We can no longer ignore the fact that the wires or these components have some characteristics of their own, right? And they'll impact the circuit behavior. So there, we cannot ignore the wave nature because now it's comparable to the wavelength. Okay, and it's important to note that even in optical fibers, these things are important because they are the dimensions. So generally, when we talk about some some micron wavelength light or some signal which is passing through the optical fiber, and if the dimensions of the fiber is comparable to that length, there again this it falls into the transmission line regime. Okay, so now if you look from the signal point of view, in one case, if you have some sinusoidal signal, and then depending on the frequency, the kind of frequencies that the signal has, it shows that whether you are in the transmission regime or lumped circuit regime or optic circuit regime somewhere, right? Another thing is, if you have a digital signal, there in general, this is how we always think of digital signals, but in reality, this is how it is. Okay, there is a net or there is a finite rise time and fall time. And what is seen is that if you write this kind of a signal, suppose some this kind of a saturated ramp signal, and you write it in terms of time, and then you do a power spectral density, what you see, it has this kind of a distribution. So the power spectral density has this kind of a frequency dependence. Okay, so this tells us that there's some frequency till which the maximum energy of the waveform lies in that region. Okay, so suppose if for your signal, whatever your signal can be, some digital signal, depending on the rise and the fall times, suppose or otherwise, if you have some sinusoidal signals, then the maximum frequency that your sinusoidal signal has. Okay, so in whatever way, if your signal has some maximum value of frequency, you can also consider that, that can correspond to some shortest wavelength, right? And then if you are in the distributed regime, so whether you are in the distributed regime or not depends on the fact that if your physical length of your component is comparable to this lambda short value, or to be specific, suppose you consider it to be 0.1 times the lambda short value. So this is just a estimation, because how much is comparable, right? So you can take it as 0.1 times of lambda short. So in those cases, you can say that you are in the distributed regime, and there the you have to consider the parameters that come because of the connecting leads or the components. Okay. Now, like here, this is just an example which says that suppose in your signal the maximum frequency is some 30 gigahertz. Okay, and now you can find so that corresponds to a shortest wavelength of 1 centimeter. So if your L, that is the length or the dimensions of your components, is more than 0.1 centimeter, more or in that range, then we have to consider it as a distributed system. If it is less than that, then you can treat it as a lumped circuit. Okay. So this is what is basically about whether your circuit is in the distributed regime or in the lumped circuit regime. Okay. Now, if it is in the lumped circuit regime, so in that case, now you have to take into consideration the fact that the wires that connects your signal will have some effect. Okay. So now what can be the effect? So basically this is how you model the effect of your connecting wires or the components. Okay. So you can say that this is how the effect can be written in terms of an inductance and a resistance, which are in parallel in series, and then there is a capacitance and a conductance, basically G, because it's a resistance in parallel, so this is conductance, so in parallel. Okay, so these four components basically defines how, and a series of, series meaning they are parallelly connected. So this is one unit cell. Now you can have multiple such unit cells, okay, over the entire region of your circuit, and that can actually help you to tell about what is the effect of your connecting leads. So what is this basically? Basically, if you think of this as something like, you can have, to some circuit where, so here you have the source, so here it's the source, and then now you have, it can go somewhere, it can be terminated, which we'll talk about later. But now what we want to see is, we want to see the effect of this wire, and we want to see the effect of this wire, right? So what what is being done here is, we are breaking the segments into this entire region into multiple segments. So we are breaking this into multiple segments, and so how much should be the length of the segment? That is given by this delta Z value. Okay, and this delta Z should be such that each of these segments can be treated as a lumped circuit, right? So delta Z should be much, much smaller than lambda short of your signal. Okay. So then if you break it in such elements, now in each of these elements, you can have contributions of these four kinds, right? So let's see what gives rise to these sources. So what's happening is, there is G, which models the imperfectness of the dielectric. What do you mean by that? So what is this? You have two connecting wires, right? Now there can be something in between, or it can be free space. So suppose if you have some coax, what happens? You have a positive, like you connect the positive terminal to one end, and then there's a negative terminal, but between them there is a dielectric, right? There's something between them. Similarly, but if you have some normal circuits, in that case, it's air. So it can be some dielectric. Now, that dielectric might not be perfect. So there can be some imperfections, which can result in some conduction current in this region, right? So not like, I am not giving a direction to it now, but you can have some conduction current in this region. Okay. So that conduction current, the effect of that conduction current, that leakage, can be described in terms of this, in terms of this G. Okay, this resistance in parallel. And then there's another thing, which is R. Why is R coming? R is coming because of, so when you talk about the wire being a conducting wire, it can have a net resistance, right? So there'll be some net resistance of the wire which you have to consider. So that takes into account the imperfectness of the conductor. Now, why do you have to consider L? It's because so there's some current which is flowing through this conductor, right? Now it's kind of a, you can think of whenever there is a current flowing through it, the resultant magnetic field, and then that can induce, that can have a net inductance. Okay. So because of that, now you have a L. So L models the magnetic field that is associated with the current. Okay. And why do we have C? We have C because what is this? This is like, this is one conductor and this is another conductor, in each of this segment. So in each of this segment, there can be an effective capacitance between the two conductors, right? So that is taken into account by the C, which is in parallel between these two wires, right? So that's how what you are doing is you are taking into effect the effect of the connecting leads. And these values, as you can see, are written in, so now it's not a fixed value, as you can see, it's written as inductance per unit length, R, which is resistance per unit length. So all of these terms are defined as something per unit time, per unit length. Okay. So it's also a function of position now. So as the current is flowing from here to here, you'll see that there'll be a net effect that will come because of the wires. Okay. So these values like this R, L, C, and G, they are distributed over the circuit and they are called distributed parameters. Okay. And now if you have infinite such unit cells, you can take into effect take into consideration their effects, and that will give you the effect of the transmission line. Okay. Okay. So before we look into how we can use these parameters, let us see that how one can go from Maxwell's equation to Kirchhoff's law. So we know that, if you consider Maxwell's equation with no time dependence now, so considering the fact that, there's no wave dependence, so no wave. Okay. So whenever you have a wave, you have a time dependence coming up there. So if you now ignore this time dependence, you get something like this, right? So from here, now this is the continuity equation. And there, now if you just look at this term, what is this? This tells you that there is no charge accumulation anywhere in the wires or in the circuit, right? And that is essentially the Kirchhoff's current law. So that's how you can come from the Maxwell's equation to the Maxwell's current law. Again, if you look at this case here, your del B del T is 0, no time dependence. So curl of E is 0. So from here, you can use the Stokes law, and this is what you get. So this is again the voltage law. So this is over a closed loop. So if it's over a closed loop, that is essentially telling you that it's same as the Kirchhoff's voltage law, right? So that the net voltage drop along a circuit, the total thing will be conserved. So this is how one can start from the Maxwell's equations and then go to the Kirchhoff's law limit. Okay. And essentially what it means is that there's instantaneous transmission across circuit elements in these cases, and there's no delay. Okay. So that's the limit of so that's one particular limit of the Maxwell's equations. Now, talking about the transmission line equations, we saw that one can model the effect of transmission lines in terms of these parameters, right? So now what we do is in each of these unit cells, the unit cell size, this delta Z is much smaller than the wavelength of light, right? So or the wavelength of the signal. So that means what it is telling us is that you can apply the Kirchhoff's law in this unit cell. Okay. And that's what is being done here. So here, what do? We apply the Kirchhoff's voltage law. So there's some voltage drop here, and then there's some voltage drop here, but that is different from what was here, right? And how different, we'll try to find out. So V of Z into T, and then there'll be some drop here, right? So minus of R delta Z into I. So some drop across the resistor. Then there's a drop across this inductor, which is given as minus L di dt into delta Z, right? And then so you are considering this loop. Okay. So then this is again the voltage that is at this end, which is different from the one at this end. So if you do that, you get, so that should be equal to 0. The algebraic sum should be equal to 0. Now you just solve it and then you take the limit of delta z tending to 0. This is what you get. So this is a differential equation of which comes from the KVL, right? Applied to this unit cell. Similarly, you can apply the Kirchhoff's current law to this node N. Okay. And if you do that, what you see is the current entering and exiting this node should remain, the algebraic sum should remain constant. So that's what is being done here, right? So so see, Q is equal to C into V, right? So C into del V del T, obviously it's function of Z, so delta Z is there. So that is actually current, right? And then, V is equal to IR, so I is equal to V by R. So it should be V into G. G is 1 by R, right? It's conductance. So that's how you write so this is the entering current, which is given as IZT, and the current that is exiting this node is minus G delta Z V. And so when you are writing V here, it's this V, right? So that's what you have used. And then minus C delta Z del V del T. Okay. And then there's this current which is leaving. So that is something also that you have considered. So this is how you apply KCL to this node. Okay. Now, if you do that, what you get is another differential equation. And this is the differential equation which talks about the current changes, right? Okay. Now, this is the most general case. What we will now do is we'll try to now apply, like make it general, make it simplified. Okay. So what we do is we consider the case where it's a lossless case. What do we mean by lossless? That R and G is close to 0. So if you put those values here, what do you see is, this term will go away. Again, this term will go away. And then you can do, derivative of one of these terms, like take a double derivative and then uh, compare these two equations to get an equation like this. So it's a second order partial differential equation that you get. Okay. And now if you look at this carefully, it's actually similar to the wave equation, right? Where now the velocity of the wave is given as 1 by root over LC, right? This is some kind of a wave velocity, and this is like a wave equation. So it's a wave equation of your voltage changes. And what is basically voltage related to? It's related to the changes in current, right? Changes in electric field. So that's how you get an estimation of, of how your voltage is changing along the line. And then you can write it like this is the solution to this kind of wave equation. We already know that. So it will be a summation of a forward moving wave and a backward moving wave with the velocity given here, right? And similarly, you can go from voltage to current, taking into account the impedance that is there in your circuit. Okay. And then, so what is Z naught? That is the impedance, which is the ratio of V to I. Okay. So in terms of line parameters, this is important that Z naught is given as root over L by C. So this is the characteristic impedance of your circuit. Okay. And you'll see that how important this is in taking into account the effect of this transmission lines. So this is a characteristic of your transmission line. Okay. And as you can see, it is given as root over L by C for lossless case. Okay. Excuse me. Okay. So now we want to look at the sinusoidal response of T line. And basically what we want to do is we want to go to the phasor representation first. So we know how to write the phasors, right? So we consider that, it's the frequency is same. So now we are not taking into account the time dependence. And we just write it as V naught e to the power minus j k z. Okay. And now if you use that form and if you use this relations, basically derivative with respect to time is what? if you consider a time dependence of e to the power j omega t, derivative with respect to time is just j omega, right? And integration with respect to time is given as 1 by j omega. So now if you use these expressions in this expressions that we just derived, you would get something like this, right? So from here, you can write your phasor representation. Okay, so and that gives you a second order partial differential, and it's something like that. So this term here is called the propagation term. Okay, and as you can see, it depends on this distributed parameters. Okay, so gamma is given as root over r plus j omega L into g plus j omega C. And it's a complex quantity which can be written as alpha plus j beta, where alpha is the attenuation coefficient. So it takes into account the fact that there can be an attenuation of the it passes through some wire, and then you have some maybe there's something, oh, just ignore the thing. So there can be some, this is your load something. Okay, but while it's passing from here to here, what can happen is, somewhere here your signal was like this, but it reduces in dimension, so there can be a net decrease in your sorry, so there can be a decrease, or attenuation of your signal. The sudden jumps are just my problem with the ink. Okay, so there can be a net attenuation of the signal that can come, and that is given by the term alpha, which is the real part of your propagation term. Okay, and then there is another factor beta, which takes into account the phase coefficient. Okay, so it's this imaginary part. So from here, this is the general represent. So if you start with an equation like this, del square v del z square equal to minus gamma square vz, you can write it as the general solution should look like this, right? Some forward going wave and some backward going wave. Okay. Now let us consider the case where you only have forward going wave. So what happens in that case? So here, as you can see, now your this term goes away. So suppose if you have just ignored this term, okay, so then you get something like this. Okay, and you make use of this expression, right? So if you make use of expression like this this differential equation and this differential equation, just ignore the noise. Okay, so if you make use of this equations, you get something like this, right? So if you now take a ratio of the voltage and the current phasors, you get something like this, right? So this is a kind of an impedance term, right? This is the characteristic impedance of your signal. So initially, what you got previously was for the case where there was no loss. So R and G was 0. But this is the general case which takes it into account all the effects. And now if you replace omega, you would get something like this, right? So this is the expression. This is a very important expression which relates the different parameters to the characteristic impedance of your transmission line. Okay. And as you can see, it's an imaginary quantity. It has this j omega terms. And so, it, like normally, not not it's not the fact that V naught plus and I naught plus are always in phase. They can be out of phase, right? And they will be out of phase if it's an imaginary quantity. Okay. So okay. So now, starting with this, we can look at different sections. 1 second, I guessed. So you can look at different cases. Okay, so first is the lossless case, right? So where you put R equal to G0, G equal to 0, and it gives you the same result as before, right? This is your characteristic impedance in that case. Okay. Another case could be when your operating frequency is very large. Okay, so omega L and omega C terms are very large in compared to R and G. So you can ignore these terms and you get a similar expression. So high frequency case is similar to the lossless case. Okay. Another important thing is this distortionless line. So what it means is that if you start with some waveform at z equal to 0 at the source, then at some distance along the transmission line, if you look at some point at z equal to L, there can be attenuation, okay, and there can be phase lag, there can be a delay, but the waveform, the form of your signal remains undistorted. Okay, so that is when does that happen? So that happens when your series time scale and the parallel time scale matches. So what I mean by that is the effective time scale of this part matches with the effective time scale of this part. Okay, so if you do that, this is the relation that you get. So L by R equal to C by G is your distortion-less line. So this is the distortion-less case. Okay, and in that case, alpha, which is the attenuation term, is given by this expression here. Okay, and Z naught equal to root over L by C is your characteristic impedance. So it's this all these expressions. So like the formula for Z naught, the formula for alpha, the formula for so this formula, okay, the characteristic impedance formula, the formula for gamma, all of these are very important for numerical perspectives. Okay. Another important thing is that if you have some wave, okay, so what is the phase velocity? We know that it's so if you have some wave like this, it's given as omega by beta, right? And so you have a similar form when your alpha is zero, right? Then basically you're in that case, if alpha is zero, your gamma turns out to be just uh, 1 second. So sorry, I just lost the formula somewhere. Yeah. So in that case, your alpha is zero. So gamma in that case becomes J into beta, right? So what is this then? It has a form like this. So in that case, the phase velocity is given as omega by beta, right? And if you use the formula for beta, and if you put it here, what do you get? You get the phase velocity as 1 by root over LC. Okay. And this is same as, this is same as what you just saw here, somewhere here, right? So this is same as what you saw here, right? So this is the formula for your phase velocity. So suppose if you know uh, the the inductance of your transmission line, the capacitance of your transmission line, or the frequency is given, and you know the impedance, right? So if you know the impedance and if you know one of the values, either L or C, you can find the other value, and then you can use it to find the phase velocity. So that's how these formulas are useful. And then so this tells you the phase velocity of your of your signal. Okay, and if there's attenuation, so if alpha is not zero, then this is how your voltage signal will look like. Okay, so that means the amplitude will be an exponentially decaying function. Okay, and you can quantify this decrease. Okay, so you can write it as so dB per meter is something. So that's how your loss is defined. Okay, loss is quantified, and this is how it's given. So minus 20 log 10 V at Z equal to 0 by V at Z equal to 1. So if V at Z equal to 1 is less than V at Z equal to 0, you have a finite loss there, and that's how you quantify this. Okay, and that's how this is related to alpha. Okay, this coefficient here. So alpha dB per meter is related to alpha natural units per meter by this expression, this coefficient. So you can again use it back to find the opposite relation. But now suppose if you are given if you are said that you know the velocity at some point. Okay, so you know the velocity at some z, not velocity, sorry, you know the voltage at some z, and then you suppose at z equal to 0, you know. Okay, and then you also know at z equal to some other distance L, right? And you are asked to find the alpha. Okay, so in that case, first try to use this relation. So this relation, what will this relation give you? This relation will give you alpha in the natural units. Okay, and then if you are supposed to find alpha in dBm, then use this relation. Okay, so remember the fact that when you are looking at voltages at different instances and trying to find alpha from this relation, you would get alpha in the natural units. Okay, and then use this relation to go to dB, right? Okay, so that was one part of the thing. Now, this is a similar kind of question which makes use of the formulas that we just discussed. Okay, so here it says that you have this TEM mode transmission line, and the distributed circuit parameters are given as this. So look at the fact that all of this is described as, ohm per meter, nanohenry per meter. So it's defined as per unit length. Okay, so that's important. And now it said that which of the case is true, whether it's lossless, whether it's lossy, whether it's distortionless, or none of the above. So can you look at the, uh, based on whatever we discussed, so you know all the parameter values. So can you tell me which should be the solution? So basically, these are the cases, right? Look at the values and try to match with these cases, and that will tell you the answer. Okay. So it's pretty straightforward. Basically, what you have to do is something like this. So for a lossless line, what we know is R and G should be 0. That's not the case here. So straightforward, this is wrong. This is not the right answer. Okay. But does that mean it's lossy? But we also have to look at this expression, right? So what the distortionless line satisfies this condition. So if you put the values, you would see that this condition is satisfied. Look at this case that, you have to be careful about the units here. Okay. So if you do that, you see that this condition is satisfied. So it's an example of a distortionless line. Okay. So that's how this, whatever we had discussed comes up in characterizing the transmission lines. Okay. This is another question which says that your resistance per unit length is given, okay, and the line is distortionless. So by that we mean that this condition is satisfied, okay, and it has a characteristic impedance of 50 ohms. So that means Z naught is given, right? You want to find the attenuation constant in the natural units per meter, okay, and then correct to 3 decimal places. So what should the answer be? So can you tell me which formulas to use? Like which way should we proceed to address or solve this question? So what values are known? R is known. We know that it satisfies this condition. Okay, and we know the value of Z naught, right? So can you try to find alpha? So how do we find alpha? Look at the expressions and see how do we define alpha. So what is the expression that defines alpha? For a distortionless line, this is how alpha is defined, right? So everything is provided to you, but you have to know how to use the relations. Okay. So this relation is there, R, and you also know Z naught, right? You have to find alpha. Any idea? Are you trying, or should I share the solution and then we'll see how? If you're trying, I'll wait for some time. Okay, let's look at the solution and then tell me if you have some doubt. Okay. So, see, this is what is provided to you, right? R by G equal to L by C. Now we know R, and the characteristic impedance is given by something like this. Okay. So from here, if you compare this two, you would see that not from here actually, rather from here, from this expression. So if you compare this expression, what will be alpha square? Alpha square will be just given as R into G, right? So if you multiply this by this, what do you get? You get alpha square, and that is equal to Rg. So alpha is equal to root over Rg, right? So this relation gives you another new relation, right? And this is this. So now based on this relations, you can try to find your alpha. Okay, so your R is known, Z naught is known. So if you use this relation, you can find G. Okay, and also you know that alpha and Rg are related by this equation. So now if you use this two, you get the value of alpha. So that's how you have to use these relations. Okay, so I'm just giving some primary examples so that you get an idea of using the relations. Okay, now till now what we discussed was the case where we had this infinite, infinite two infinite conductor system, okay, transmission lines, and we did not consider the fact that what happens when you have some load or some termination at one end. Okay, so if you have some kind of termination which has some, load impedance of ZL, okay, so how do we deal with those cases? So there we take the load as, so this point as Z equal to 0, okay. And if your transmission line or the connection leads has a length of L, then the source will be at Z equal to minus L. So there, in this cases, so it's important that why do we have to look at it separately is because, see, you have some V here, okay, and then there'll be some, some voltages, suppose here, some voltage difference here, but just a little bit from in the towards the right, and what happens is that the voltage becomes equal to, or this that just depends on the impedance, right? So how do you ensure that the connectivity, or the continuous nature of voltage and current remains conserved at this end, where here this at this end it's only, it looks like it's only controlled by this load impedance. So practically, it's not just the load impedance that matters, okay? The transmission lines also matter, and there we have to bring in new boundary conditions to ensure that things remain continuous, okay? So what we do is that we consider that in cases where this ZL, okay, this ZL is the impedance at this terminal, right? But somewhere a little bit here, what is the impedance? It's in general given as some V naught plus by I naught plus, right? Something here. So something at the starting is Z naught, and then it gradually proceeds, right? So if they don't match, if this impedance don't match, in general, they might not match. So there we will have to consider a reflected wave, right? So what we say is that the general form of voltage in that case is written by something like this. We have this plus term shows some forward moving wave, but you also have this reflected wave, okay? And similarly, you can have the current. Now, one important thing here is that initially, when we discussed about the forward wave, we saw that the impedance is given by this, right? Some Z naught, okay? But then for only backward moving waves, so if you now consider only this part of your wave, okay, there you'll see that it is given as minus Z naught. So that means the impedance of the forward and the backward waves differ by just a minus sign, okay? So that's what is being replaced here. And then, so you can go from voltage to current, okay? Now let us see how we apply the boundary condition. So at the load, what should happen? So your voltage and current is a function of Z. So Z is along this line, okay? So I don't know why this is sudden jumps. So just ignore. So Z is along the horizontal direction, okay? So in this direction, so this is your Z. Just consider this as this line, along this line as Z. So then V at Z equal to 0 and I at Z equal to 0, the ratio of them should be equal to this impedance at this terminal, right? So that is one boundary condition, right? So if you apply that to this expression here, what do you get? See, what is the ratio of V by I in general? And then you put Z equal to 0. Okay. So you get something like this, right? So from here, what you see is you get an expression like this. So ZL is related to Z naught. Z naught is something which is at the source. Okay. And then they are related by this relation where you have this additional term now, which is this. This is called the reflection coefficient. Okay, it's the ratio of the reflected wave to the the forward moving wave. Okay, and you can also write it in terms of your load impedance and the impedance or characteristic impedance of your transmission line. Right. So this is one boundary condition. There's another boundary condition which needs to be satisfied at the source. Okay, at the source meaning that should be equal to Z equal to minus L, right? So now when you write Z in, this is the impedance at the incident site. There that should be equal to ratio of V by I at Z equal to minus L. So in this expression, you put Z equal to minus L, find the ratio, okay? And then if you solve it, you would get something like this. So this is interesting because now what this tells you is this is the impedance at the incident site, right? Here. This is how the impedance looks somewhere here. But that impedance value is dependent on the load. Okay, that is dependent on the load impedance, and that is also dependent on the length of your connecting lines. Okay, so the load impedance and the length of the transmission line affects the impedance that is seen at the source. This is a very important observation or very important fact. Okay, so this is what happens when you have this kind of a terminated lines. Okay. So now for lossless case, you can just try to look at the different cases that can arise depending on the values of, beta, ZL, Z naught and all that. Okay. So this is the general form. Now, if it's a lossless case, then your gamma is equal to J beta, right? You don't have alpha there. So if you replace that, you get something like this. Now look at the different cases. Okay, so if ZL is equal to Z naught, that is the load impedance matches your characteristic impedance of your transmission line, then your the incident impedance is also equal to Z naught. Okay. Now what happens when you have ZL equal to 0? That means short circuit. Okay. Then you have a dependence like this. So you can see that depending on the value of your, length of your transmission lines, these values will differ. Okay. And it can diverge at points. Now again at ZL tending to infinity, what happens? So it means it's an open circuit now, right? At the load end, it's open. So there you again have this kind of a minus J cot beta L into Z naught kind of dependence. Okay. Now, when beta L tends to 0, so that means there is a dependence on this length, right? So now depending on what beta L is, or particularly what the length of your transmission line is, multiple cases can come in. Okay. So if beta L tends to 0 or pi, you can see that Z in is equal to ZL. So it matches with the load impedance. But when beta L is equal to pi by 2, that means, when length is given as lambda by 4, that's a very interesting case because now you can see that Z in, okay, it's different from ZL and this is how it's related. So it has a dependence on the characteristic impedance of the line and inversely related to your load impedance. Okay, this formula is or this relation is very important. Okay. So this relation is very important. And this comes up when beta L is equal to pi by 2. So that means when L is equal to lambda by 4. Okay. So lambda here is the shortest wavelength of the signal that you have. Okay. So now let us look at some typical questions. Okay, the input impedance of a short-circuited lossless transmission line, quarter wavelength. Quarter wavelength means lambda by 4. Okay. So the input impedance, you want to find the input impedance. So Z in you want to find of short-circuited. Short-circuited means ZL is equal to 0. Lossless transmission line wavelength is, right? So it's short circuit. So it's ZL equal to 0, right? And then you want to find the input impedance when beta L is equal to this, right? So then this is your expression, correct? So let's look at the solution now. You can look at it as something like this, right? It's basically this expression. This is what we saw, right? Now what it is said is that it's short circuited, right? So short circuit means ZL is equal to 0, right? This is the expression for the case when the transmission line has a quarter wavelength length. Now you have to put the condition that it's a short circuited transmission like end. So in that case, ZL is 0, right? So now if you put ZL equal to 0 here, what happens? Zn becomes infinite. So the answer should be C, right? Okay. Now, this is something which is similar to one of the questions in your okay. So this is something which is similar to one of the questions in our in your assignment. So there are some different values, but basically similar question. Okay. So what is this telling you is that this is some signal where you know Z naught in this part. So Z naught is the characteristic impedance in this section. You want to find the characteristic impedance in this section. Okay. And then finally, you also know the characteristic impedance of this section of your circuit. Okay. You know the load impedance. So the load at this end is given as 150 ohm. This should be ohm. So 150 ohm. Okay. And you also know that the transmission line length of, of these sections are given as lambda by 4. Right. You have to find Z01. That is the, you can say the characteristic impedance of this section. Okay. Keeping in mind the fact that there is no reflected wave beyond A, beyond this point. Okay. So first, can you tell me how to proceed with this question? So where should we start? From the load. Okay. So how do we start from the load? What do we know at this end? We know ZL. We know that the transmission line length is given as lambda by 4. Okay. We also know the characteristic impedance in this section that is given as Z02, that is given as 30 ohm. What we want to find? We want to find what is the Z in at or the incident impedance in this section, right? And that incident impedance will serve as a load for the for this part of the circuit. Okay. So you want to find Z in, right? You know Z naught, you know ZL, and you know that it's the length is given as lambda by 4. So can you find the Z in for this part of your circuit? Okay. Five. Okay. Why do you say it's 5? 30. So one second. We need to use similar relations, right? Z naught is known. ZL is known. So let's see how much it comes out to be. 30 into 30 by 150, right? Right. So it should be 6. So that's the incident impedance in this part of the section. And that appears as a load for the circuit, part of the circuit before it, right? So now let us look at this part of the circuit. Okay, here you know ZL, that is 6 ohm, right? And you want to find the characteristic impedance of this section. Okay, and you also know the length of your transmission line. Now, in order to find Z01, what do you need? You need to know the, you can say the Z incident of this section, right? So if you look at this formula, because this formula again holds, because the length is again lambda by 4. Now here, in this, for this part of the circuit, you know ZL, okay? You want to find Z naught, which is the characteristic impedance of that section. So for that, you need Z in, which is the incident impedance in this part of your circuit. Now make use of the fact that there is no reflected wave present beyond A. So what does that mean? When there's no reflected wave, that means the impedance that you have at this end should match with the impedance that you have here. If the impedance don't match, there'll be a reflected wave, right? The fact that there is no reflected wave beyond A tells us that the Z incident in this part of your circuit is equal to 100 ohm. Okay. So now if you use that relation, you can use this same relation. So now your Z in is 100, your ZL is 6. You want to find Z naught. Okay. So can you do that? That will be your value of Z01, right? Right. So basically, that's how this kind of questions are to be addressed. Now, in another kind of problem, you can have situations where now you know the voltage at one end, okay? But suppose if you have some resistors somewhere here, okay? So you know the potential here, difference here, you know the voltage here, and then you have some voltage here, you have some sorry, what am I saying? You have some potential difference here, okay? And then you have some resistance in this path, and then there is some another net impedance in this part, okay? And they are connected by some line. You know some, this is, you know the put, sorry, you know this is just voltage. I wanted to write V. So you know the voltage here. So how do you solve those cases? So there, depending on the ratio of your impedance, it's pure. So all the Kirchhoff's law holds in all this individual sections, right? So now, or the voltage dividing laws. So here, depending on what the impedance or the resistance values are in these two sections, your voltage that you have here will get divided. Okay. And that can help you in different kind of questions to find the voltage. Suppose if you know the voltage here, you know the resistance here, you want to find what should be the voltage here, right? So in those cases, you can also make use of the voltage dividing concept. So the voltage gets divided between the two resistances depending on the ratios of the resistors or the impedances. Okay. For this question, it is something like this. You find Z in, okay, and then you look at the first section, which is uh, which is this part of the section. And if you use that, you get something like this. Okay. Now this is the final part of today's class, where there's another thing that can happen, that is standing waves, right? So for lossless lines, you can write the net voltage as something like this, right? You have a forward moving wave and you also have a backward moving wave, and they are related by the reflection coefficient. And this is how you can write it. Now, the reflection coefficient can be imaginary, so you can write it as something like this, some modulus into e to the power j5, where phi is the argument. Okay. So now if you use that, there can be several cases. One case is when ZL is equal to some n times Z naught. Okay. Then you can see this is how the reflection coefficient looks like. Okay. What happens when ZL is equal to Z naught? As you can see, your reflection coefficient goes to 0. So this is the concept that we used in this section, right? So when these two match, then there is no reflection. Okay. Now, what happens when you have a short circuit? In that case, your reflection coefficient is equal to -1. So that means the argument, the phi L term, should be equal to pi. So if you use that in this expression, you would get something like this. And now if you look at the total, this is just the phasor term. Now if you look at the net voltage expression in which has both space and time dependence, you would get something like this, right? And this is basically a standing wave. So you can simplify it further using trigonometric relations, and you would see that it's actually a standing wave. It's not a propagating wave. When you have cos omega t minus kz, sin omega t minus kz, those are all propagating waves. But here you have standing waves. Okay, so this is a kind of standing wave that generates when you have this condition. So when it's a short circuit, okay, and in the lossless case, you can get standing waves. Similarly, when you have infinite, so when ZL is infinity, that means when you have open circuit, even in that case, you have standing waves. And you can see that if you look at it, this is how your voltages will have maxima and minima depending on the length of your transmission lines. Now, what happens when your reflection coefficient modulus is not exactly equal to 1, but it's slightly less than 1? So there you would have the voltage dependence as something like this. So you would see that the maximum value is not equal to 2 V naught and the minimum is not equal to 0. This is the case what happened here, right? But in this case, you would see that the maximum doesn't reach to V naught plus and the minimum does not reach 0. So the ratio of maximum to minimum is what we call the standing wave ratio. Okay. And that is denoted as S. And you can relate S with your reflection coefficient by this relation. So now given the reflection coefficient, okay, one can find S using this relation or vice versa. So if you know S, you can find the reflection coefficients. Okay. So basically that was it. Thank you. If you have any doubt, you can ask me. Okay. So if not, thank you. Thank you.